Right, so as an immediate consequence, we have the Bell theorem. Which is saying that the local correlations form a, so they can be represented, they are quantum correlations, all of them, but they do not exhaust all quantum correlations. Of course, the reason here is that if they were the same, then the values of the game CHSM will be the same, but they are different. The quantum value is strictly larger than the local one. All right, so let's see now. We have this inclusion here. So that's a strict inclusion. Until now, we have the inclusion also in the no signaling class, the whole no signaling class. And how about this inclusion here? Do we have also strict inequality there? Well, yes, we do. This is not difficult to observe. In fact, the CHSH game has a perfect no signaling strategy, or in other words, put the value, the no signaling value is 1. And here one can try the strategy that is, here is just saying which one that will be. This will be a half if xy is a plus b, and 0 if not. And not surprisingly, so this is a no signaling strategy. One needs to check that this is indeed no signaling. So, right, so we have, therefore, inequality here as well. And then let me now once I have arrived at this chain, let me remind you of the CQ class as well, rather QC class as well, that was defined by Sergei. So the QC class, quantum commuting class, they are correlations. This is just a reminder, a quick reminder of the following type, where these are again POVMs. Now they act on the same Hilbert space. I use just operator multiplication here instead of tensor product, and they commute with each other. The E's commute with the F's, but the E's, of course, between themselves need not commute. That's the whole point of yes.
Can I just clarify, what's the dimension of the Hilbert space now?
Right, so it's arbitrary dimensional Hilbert space. This act on H, Hilbert space H of some dimension. Yeah, some Hilbert space on the same Hilbert space H, and C is again a unit vector in the Hilbert space. Exercise, right? Exercise. If you have a finite dimensional Hilbert space here, then this implies that the correlation is of quantum type immediately. So if they're represented on a finite dimensional Hilbert space, both of them, you have up to entirely equivalence. You can split your Hilbert space as a tensor product. You can split your E's and F's as tensor products as well. Right? So actually, that's a kind of a nice kind of way to view the Q1s. They're just the ones for which they're QC for which the Hilbert space is finite dimensional. Let's say. Right. All right. So these are the QC, and then we have the inclusions. And let me remind you also that the QA was the closure of the Q class. This is the same as the closure of what Sergei called QS, the quantum spatial correlations. Right. Right. So now, moving to self-testing, the question that is the starting question here is the following: given a correlation arising from some model M, can we recover the model M? And of course, this is not always true. At least there are some operations that can be performed without changing the correlation. Operations on the model without changing the correlation. For example, starting with, so the first way to have the same P without different M is starting with these POVMs, right, and then pushing them with an isometry somewhere. and pushing your vector as well, summating to some other Hilbert spaces. So you will obtain a certain model that will give rise to the same correlation. So definitely, at least some unitary equivalence is needed to kind of to model out. The other thing that you can do is starting with your model M, you can kind of artificially add a trivial part. So you have your XA. Remember, I will tensor it with some auxiliary space, finite dimensional still. HB, I will tensor with some other auxiliary Hilbert space. My P of M's will be tensored with the identity. And my vector C will be tensored with some auxiliary unit vector. And this auxiliary one will be a unit vector in the tensor product of the auxiliary Hilbert spaces. This model again will give you the same correlation. So obviously uniqueness is not kind of, the uniqueness of the model cannot be kind of, these operations you need to model, to mod out. But up to these two operations, actually, you have hopes to have uniqueness. And this is what self-testing is about. So definition of local dilation. If you have two models, so say M and M tilde. So M will be page A, page B, E, X, A, F, Y, B, and C. And here, this one will be with tildes, right? Everything with tildes. So let me not repeat those. We say that M tilde is a local dilation of M. And we write it like this. If I can find these auxiliary spaces, Hilbert spaces, so we are talking about quantum models until now, not quantum commuting. Everything is finite dimensional. If I can find auxiliary spaces and an auxiliary vector, such that, and also I can find some isometries. So U sub A will be from HA to HA tilde, tensored with auxiliary. UB from HB into HB tilde tensored with auxiliary space, such that if I act first with the original model P of M's on this vector, and then afterwards I apply this local unitaries to this vector. So now I am at the tensor product of these four Hilbert spaces. I will have to obtain, that will be the same thing as applying my P of M's of the second model M tilde to my vector C tilde, tensored with the auxiliary vector. So this I want to have for all C and A, X and A, and Y and B. And in particular, this would imply as well that if I apply to the vector C, I will recover C tilde, tensored with the auxiliary. And now, right, so that's, of course, that's a special case of the first. Let me say this is for all X, Y, A, B. And then note that if M tilde is a local dilation of M, then the corresponding correlations are the same. And we call a certain M tilde, I will call it now, a model, self-test. So M tilde is rather not M tilde, but the correlation coming from M tilde. if I can revert this, so in other words, if every time I have a model which gives me the same correlation, I must have that M tilde is the local dilation of M. So the correlations that are self-tests are kind of the ones that have unique, up to these operations, of course, let's say, unique representation, unique model that gives them that. Roughly speaking, unique model that gives these correlations.
So the left-hand side is symmetric?
No, it will not be the relation of dilation. Sorry, say?
Yeah, so PM equal to PM twiddle is the same as PM twiddle equal to PM, but the right-hand side is not symmetric.
No, so yes, exactly. So I want just one to have this property.
Right, okay.
Yeah, I just want to have one model that satisfies the property that anything else that gives this correlation must be contained in it. So it's a maximal, right? It's a maximal element of the model. So let's say this is a partial order. This dilation, kind of local dilation, is a partial order. So I'm talking about a maximal element, choosing existence of a maximal element in the set of models representing a correlation. All right, so do these things exist even? So CHSH game again gives example of a self-test. In fact, the correlation that wins, that achieves the optimum for the quantum value is a self-test. So this is the theorem here. And now I will reveal to you, right? So I will reveal to you why there was this question, why are these vectors that I selected, these PVMs, why do they work? And this is the reason why they work. So first of all, models I can equivalently, as I said, represent using the corresponding symmetries, the unitaries, instead of just writing the PVMs. So the model, so the correlation P for which achieves the quantum value of the CHSH game is a self-test. Okay, so I will give the sketch of the proof. What is really the thing that makes it work? So what makes it work, we will see, is exactly this kind of sums of squares thing for the model operator, or 2 times square root 2 minus the model operator. So sketch of proof. I will need to exhibit an ideal model. So the ideal model, so I claim this is called, okay, so I didn't define that. This M tilde is called an ideal model for the correlation. So this is this M tilde, the maximum, a maximal element in this partial order. So this will be the following M tilde. M tilde will be C2, of course. C2, right? Everything is two-dimensional there. Here I will have the 2 operators that will play are the Pauli matrices. This is for the Alice side. Remember, this is kind of A0, this is A1 for Alice, and they split in kind of spectral decompositions. These are the corresponding PVMs for Alice. And for Bob will be a rotation of this. And here I will have the maximally entangled vector.
So I'm slightly confused, but is this just a way of rewriting what we...
So I claim, yes, so for the, I already know that this model gives me a correlation that achieves the quantum value. This I already know.
The question was that this is just the same that you wrote before using V0, V0 star, right?
Yeah.
Yes, exactly. Very good, very good. So exactly, the spectral decomposition of sigma x is the first POVM, the 0th POVM of Alice. Of sigma z is the second POVM of Alice, and similarly for these 2 operators on the both sides. Yes. So exactly. So because of this, I know already that this correlation achieves, the corresponding correlation achieves the quantum value, is optimal for the quantum value. So now the question is, why is this a maximal element? So here, sigma x and sigma z are these matrices. So I know already from the previous computations that this P is exactly, this arises from this model. So now suppose that I have another model, I need to kind of include it into that one, into an amplification of this one. What is happening is something actually very, very pretty. So let now M be another model, giving the same correlation. Now going back to the model operator and to the and to the relation that I have between the model operator and the value. And maybe this is the time really to stop. And actually, yes, no, not the lecture. Martin asked me maybe to make a comment on the last question, which I forgot when I started. The relation that I'm using can be written for more general games, not only the CHSH game, but we do not have the split of squares, factorization and sums of squares, so therefore we cannot estimate or evaluate precisely the value. So the relation that I'm referring to is this one, that this relation one can write for more general games. Similar relation one can write for more general games. I can find an equivalent kind of analog of the model operator and have a similar relation. Right, so because this is achieved now for this correlation, I know that this must be equal to 2 times square root of 2. However, 2 times square root of 2 minus beta m, it had this really nice kind of sums of square decomposition, right? So this is applied to Xi, this must be equal to 0 now. All right? So now this is a sum of 2 squares, right? I had them, I shouldn't have erased them, but I did already. So this implies that each of those individual terms, when applied to Xi, must be 0. So what does this mean? This means that the following is true. Tensor with 1 plus minus 1 tensor with B0 applied to my Xi is 0. And also this is 0. And now I take these relations and I no, that's all motivated. It's not like out of the blue. These two operators, they satisfy the following. So they generate a group, the Pauli group, which is just plus minus the identity operator, plus minus sigma x, plus minus sigma z, and plus minus the product. So crucial relation here, why is this a group? Because if you multiply them the other way around, so they anticommute. All right. So I'm trying to mimic the same relation for the elements of my new model operator, which was an arbitrary model that is giving this particular correlation. And indeed, this relation, they do allow me to do that, because if I form identity times B0, B1 plus B1, B0, let's say, applied to Xi, using these relations, I will first throw this B1 to the other side with A0 minus A1 divided by something, square root of 2. Then afterwards I will throw the B0 to the other side as this operator. Similarly, I will do the same thing on the other side, throwing first B0 and then B1. But when I will be left with some kind of formula on the left side only, the right side will be the identity. right? This times this plus this times that, right? It will be 0. So this is 0. Yes? Raise, yes. Thanks. Yes, thank you. Right, so now another small reduction here is that the vector C, which we do not know what it is, but it can be assumed to have a full rank. Remember the Schmidt rank that Gemma was talking about with defining. This vector C is a bipartite vector. It can be assumed just by very simple reduction to have full Schmidt rank. But this, of course, means that in that case, that this whole operator is 0. So I have the anti-commutation relations for the operators B on the both side. Similarly, I have the same anti-commutation relations for Alice's operator. So they give rise to a representation of the Pauli group, right? This is a Pauli group. This is the defining relation in the Pauli group, but there are not many of them. So in fact, the irreducible ones, of course, will be split in sums of irreducibles, right? This corresponding representation. We'll have maybe some abelian part, which is not present here, and then we will have some multiple of the identity representation of the Pauli group. So this is how you arrive at these isometries. So UA will give me a kind of unitary equivalence of the representation of the Pauli group starting from plus minus the identity, plus minus A0, plus minus A1, plus minus A0, A1. Ah, yeah. Sorry, yes. I forgot. Yeah, sorry. So it will be brought to the Pauli group amplified, right? So this will be the identity on 2 dimensions, tensor with some dimension, and here I will have the sigma x, right, plus minus, everywhere. Sigma x tensor with some dimension, sigma z tensor with some dimension, and plus minus sigma x, sigma z tensor with the same dimension. So similarly, I can kind of rotate the B operators, but I will not want to rotate them into the same. That's useless. I will rotate them because this is what's suitable to an amplification of this representation of the Pauli group. This is another representation. And then this will be my operators, and why the vector will be right. So what I want to achieve at the end of the day is when I apply this to my vector C, I need to get the maximally entangled vector tensored with something, auxiliary vector. This auxiliary, of course, will live in the corresponding tensor product of the amplifications. Why is this true? Well, because this vector here, it will turn out to be an eigenvector of the amplification of the sigma x tensor sigma z plus sigma z tensor sigma x. So there is a little computation here that I'm not making, but this is why I had to rotate to this specific one, right? The other one will be useless, as I said, of course. Right. So yeah, this is why we have a self-test in that case.
Is there some uniqueness statement about the maximal elements?
No, not that I know of. Not that I know of. No, exactly. So they will be included in one another. So right, I mean, up to this kind of partial order, they will be. If you module out the corresponding.
They are just mapping the vectors. They are not mapping the operators.
No. They are not making operators. This is the whole point. Yeah. This is the whole point. Exactly. Actually, that's indeed a crucial point. They're only on the vector. These relations are only on the vector, not. Yeah. So in a sense, here we have something stronger because we have equivalence of the whole representation, not only on the vector. So that's why there is scope that self-testing, and it does hold in other cases, right? But this is a lighter thing that we want.
So again, maybe a terminology question. So what is self-testing? Because in a sense, like the definition you gave, you just gave. Do you talk about the model being a self-test?
So there are two views
here. The correlation.
Right. So there are two views. So in different papers, you can find both things somehow, right? So usually it's the correlation P. The P, you say it's a self-test if it admits an ideal model.
Okay.
Yeah. If there exists a model which is the maximal element among all
Because in this proof you just showed that this particular model is a maximal model, right?
Right, yeah, exactly. So self-test means there exists one. All right.
Maybe a question about what's written here, the definition of this pre-order. Are you not conjugating the operator by u may against the u p? I only see u may against.
Right. So let's be careful here. So I want to. So this is acting on the side of the model M. I am pushing it forward with some isometry, and I'm getting on the side of the model tilde, the tilde one. So I think that that is right. Yes, I'm not conjugating. Sorry.
There is a second.
Over here. All right, right. Yeah. Okay. Very good. Very good. If you replace this, so this identity implies the second one. If you replace my vector here with this one, you will see a little bit of conjugation. Correct. Yeah. Thanks. Indeed. Yeah. Yeah.
So is it possible to have for one game to have multiple self-tests that are different?
It's not about a game, so it's about a set of strategies. In general, it doesn't have to do with them. If you find maybe you find a game for which the optimal strategy is, it's not a subject. It's not it's not an attribute of the game. It's an attribute of a set of strategies. So you can talk about self-test within a certain set of strategies. Here is the most simple case where it's a self-test within CQ, within all quantum strategies.
But then could it be that there is some other PD in CQ that is also a self-test?
Yes. Their examples, so Laura, Chris Schaffhauser and collaborators, William Slofter and collaborators, they're recent examples. So that's why I said in the beginning there is kind of revival in the interest of self-testing. There are actually several papers, recent papers, dedicated to this, yeah, with more examples, yes. All right, so I had a very ambitious kind of plan because this was the end of the first lecture, so I'm now starting the second lecture. But I was lucky that Sergey was talking before me and he introduced all these things, so many of those actually I don't need to introduce. So Sergey talked about the exactly about the. He introduced the sister algebra that I will be kind of working with now. And let me remind you what that is. So here I kind of agree that this will be my input sets, this will be my output sets. Let me denote by d sub A the diagonal. So this is A by A diagonal matrix algebra inside M sub A, which is the full matrix algebra. So the algebra that I will be kind of interested in is the free product. Let me introduce it through the universal property first. So this is universal sister algebra generated by projections, orthogonal projections, EXA. So these are certain relations on these generators, and the other relations are that if I add along A, I get 1 for every X. So this is just kind of the PVM property, but abstractly. So this thing exists because we have many representations of those, and this is what exactly Sergey pointed out. Which are those? Well, every time you have a certain bunch of PVMs acting somewhere on some Hilbert space, you generate a sister algebra out of those. This will be a concrete version of these relations. So just by abstract kind of nonsense, you can take kind of a family, separating family of such things, take a completion, right, with it's completely represented. You have a universal system algebra, which has the property that the star representations on some Hilbert space, so this star representation, correspond to families of PVMs. Alternatively, one can, as Sergei pointed out, this can be just taken to be the free product. He defined the free product of is a group system algebra of a free product. But alternatively, one can say that this is, by taking Fourier transform, this will be the free product of the corresponding diagonal system algebras, diagonal matrix algebras. So I will have X of them. I will have X of them. I will take the free product, and they will be all kind of, the units will be shared. The unit will be shared. So this alternatively is the system algebra that gives me this universal system algebra for these relations. So let's have a look at now which are the, on the other hand, the unital completely positive maps. Right, so first of all, let's observe that if I have not the PVM, so I just want to say a few words about the disambiguation now. Right, so this is the story is about that. If I have a POVM now, instead of PVM, that's family of those, what I have instead is just a family of UCP maps from the diagonal matrix algebra to B of H. So these are acting on H. So this is just a UCP map. By sending the canonical basis here to the corresponding element EXA. And now by a non-trivial theorem, you can glue, as Sergei again pointed out, you can glue UCP maps to free products. So this is Bocca's theorem. You can obtain a UCP map on the whole algebra AXA to B of H, which on the generators, this abstract kind of gadgety XA gives me just capital EXA, the complete thing. One consequence of that you can simultaneously dilate, because UCP maps, they dilate to star representations via Stein's-Pritz theorem, explained by Gemma, right, mentioned by Gemma. So therefore, every complete family of POVMs dilates to a family of PVMs simultaneously. All right, so now the same thing can be done on the other side, of Bob's side. This is Alice's side, on the Bob side. And now I wish to consider the maximal tensor product of these two sister algebras. And the theorem, again, underlying the last result that Sergei was giving the proof. And I'm very lucky that his hand waving involved a lot of chalk use, so I do not need to, I need to kind of spend a lot of time on this. But if you have a linear functional, so if you have a certain linear functional on this algebra, or even the algebraic tensor product, I can obtain a certain bunch of scalars, P, A, B, given X, Y. I just estimate this linear functional on the canonical generators. Let me call F, Y, B, the canonical generators of the Bob's algebra. And now, the theorem is that P is of quantum commuting class, precisely when I can find a state S on the maximal tensor product. Such that, let's call this P sub S, A, B, X, Y, so that P is equal to P sub S for some state on this maximal tensor product. It is of QA class, if and only if I replace the maximal by the minimal tensor product. So this is just not just kind of translating just for the sake of translation of different things. This will be the stepping stone that I will need for the NPA hierarchy that I want to talk about shortly. Before that, just a few comments on why this is true. Right, so let's see. If you have a representation of P as a QC correlation, So just a brief kind of sketch of the proof. If P is arising as in the definition of QC correlation, then it becomes clear here that these are POVMs. So they give rise to unit of completely positive maps on the Alice's and the Bob's universal algebras. So I have some map on Alice's side. H is the space where they both act, and some UCP map on Bob's side. And then they have commuting gradients, so therefore I can multiply them. P dot C is a UCP map on the tensor product here. So this is just obtained by sending elementary tensor to the product of the two operators. That's a UCP map, and clearly just rewriting that. So P is P sub S for S given like that. I have this P dot C applied to my W, and then I apply this vector state to it. So it's a state, it's arise from a state. Conversely, so this is in one direction. Conversely, if you are given, on the other hand, a state, you just perform GNS. So given a state S on the maximal tensor product, perform GNS to obtain complete operators which represent your correlation. One consequence of this argument is that you can do, so the disambiguation that Vern was, I mean, he coined this term very nicely. So one can see immediately this disambiguation on the QC level. Every time you have a representation of a QC correlation via POVMs, you can also represent it via PVMs simply because of Steinspring's theorem. There is a Steinspring dilation, right, of the UCP map to a star representation. All right, so a short word about the QA. The QA relies on the fact that, first of all, if you have something from the Q, it's just split tensor form. Of course, it gives you a split tensor form of the minimal tensor product. So Q, everything that is in the Q class here arises as a state on the minimal tensor product. The state space is fixed or closed, so you have everything that is in QA arises as a state. Conversely, if you have a state, why is this corresponding correlation, state on the minimal tensor product, why is the corresponding correlation in QA? What lies behind this is that any state, so you represent your algebras completely on H and K, so they live here. So you can assume that they live here. Right, and the closure of this is equal to my minimal tensor product. And then you have a certain functional state on this. You can obtain the state as the limit of convex combinations of vector states. So this is nothing to do with tensor products. This is true in general, right? If you have a state on a certain kind of sister algebra represented concretely, it is the limit of convex combinations of vector states. So vector states, when you have vector states on the other hand, then you're basically again in the realm of Q. So right, so in the remaining 5 minutes, let me prepare the ground for tomorrow morning, I think. The remaining 5 minutes. So I want to move to NPA hierarchy based on this. So what is NPA hierarchy? So NPA hierarchy, it represents the QC class, which is difficult to compute, presumably, as an intersection of graded classes. So here you will have for every given K, you will have a subclass of the QC or superclass of the QC class, and the elements in this kth grade, kth level, they are verifiable efficiently. So the underlying question here is the following: starting with P, a correlation, no signaling, let's say, is P in the quantum commuting class? And this is a hard question to answer. One way to see it, to try to answer it, is the MPA hierarchy. So you're writing down your acoustic correlations as an intersection, infinite of course, but intersection of sort of efficiently computable or verifiable classes of correlations. And if at some point you realize that P is not in one of those, then there is no chance that, of course, P is not in the QC class as well. So it's a method to decide when a correlation is not in the QC class. It's not an efficient method to decide when it is in the QC class. So if P is not in C, the kth grade of these correlations, then P is not in this. And this one here is verifiable, let's say. Right, so what is the base of this? What is, how are these classes obtained? This exploits the following fact. The positivity in assisted algebra is something that has two phases. One of them is the spectral phase, the other one is the algebraic phase, let's say. It relies on the algebraic characterization, if you wish, of positivity. So in assisted algebra A, U is a positive element precisely when it factors as V star V for some other element V. So we are trying to exploit this. We are trying to see when a state, so by virtue of this theorem, the QC class will arise from states on the maximal tensor product. Now the maximal tensor product here, these algebras are finitely generated, so they're generated by words. So if I take the words W, let's say, which is just the words on the generators, so this is some E's, right? Some E's up to some point, some F's up to some point, right? So this is a word of generators of the maximal tensor product. If I verify the positivity of the state on polynomials of the form P star P, where the degree of P is finite, say less than or equal to K every time, this is enough for me to verify the positivity of S on the completion. This is not true for every sister algebra. This is exactly the point where the special kind of form of this sister algebra takes place. It's not a general statement. You can know this generally. What is lacking is the order boundedness of the cone that's arising from the split forms. Such cones are not necessarily order bounded. They are not necessarily bounded by the identity. If your algebra is not a sister algebra. If you just have a general star algebra, this is not necessarily true. However, in our case, this is true. So to check that a certain linear function on this maximal tensor product is a state on the maximal tensor product, it is enough in our case to test its positivity on such polynomials. So I want to check the positivity for this for every k, for every fixed k. And here the degree of p is not more than k, and p is just a polynomial on these words. Degree means the maximal length of a word that participates in my polynomial. So p has just some coefficients lambda, these are scalars, lambda sub u times u, where u is a word, and the length of u is not more than k. Right, so fine. The time is really getting almost. I'm almost done. So yeah, time is finishing. So this is the base of the MPA hierarchy. So next time, tomorrow morning, I will kind of prove why this is the algebras. You can use this test, and this is an efficient test. This is about positive semi-definite matrices and completions of positive semi-definite matrices. So that's why it becomes kind of easy to compute these CK graded correlations. I should say that this is not in the last 6 seconds. It is not the original presentation of the MPA hierarchy. This is a one that we Vern and Simone and Andreas Winter and Dan Stalke kind of came up with, I think, independently, it was before, but we didn't know about that. So this is kind of a slightly different presentation, more operator algebraic one than the original one that you will find in the APA paper. All right, so I'll continue tomorrow.
Time for a question or a comment.
So I don't know if this will be explained tomorrow, but how do I, so I'm given, in a sense, a correlation. How do I evaluate that on a polynomial? Like on EXA tensor FYB, I get what the value should be.
Right, yeah.
But on something else,
absolutely true. So basically you can extend it any way you wish to the algebraic tensor product here, right? If you wish. And then you can impose on these all possible extensions different positivity properties. It will be a graded positivity properties, kind of stronger and stronger positivity properties by requiring this for fixed degree.
And so the seminar optimization you were talking about is finding the extension that actually makes it possible.
I mean, finding, so you do not need to extend it, yeah, I understand your question. So you do not need to extend it to the infinite dimensional thing. It's enough to extend to the finite dimensional thing generated by polynomials of degree at most k. That's enough. This S, when it's tested on degrees at most k, does not need to be defined on the whole infinite dimensional thing.
And so you say it doesn't work if you are unable to extend it in any way to the things for degrees at most.
Right. So if at some point you see that your extension, none of your extensions satisfy the positive semi-definiteness that you're after, then it is not a correlation of your QC type. Yeah.
So I see no other raised hands, so let us thank Ivan again.